For roughly 2 decades, quantum computing has carried an unfortunate and somewhat embarrassing reputation in the tech world, being described year after year as perpetually 5 years away from actually mattering. That reputation appears to finally be shifting in 2026, and not because of hype or marketing, but because of a genuinely significant scientific paper published in the journal Science earlier this year. Researchers from some of the most respected physics and computing institutions in the world, including the University of Chicago, Stanford, MIT, the University of Innsbruck, and Delft University of Technology, came together to make a specific, carefully argued claim that quantum technology has reached an inflection point comparable to the earliest days of classical computing, back before the invention of the transistor, completely reshaped what computers could become. In this video, we are going to walk through exactly what this claim means, why serious scientists are making it now rather than years ago, and what it does and does not tell us about when quantum computers might actually start changing everyday life. To understand why this comparison to the transistor carries so much weight, it helps to remember what computing actually looked like before that invention existed. In the earliest eras of electronic computing, machines relied on vacuum tubes, bulky, fragile, power-hungry components that worked well enough to prove the fundamental concept of electronic computation was possible, but were far too unreliable, expensive, and physically enormous to ever scale into the kind of computers that could fit on a desk, let alone in a pocket. The invention of the transistor in the late 1940s did not immediately produce modern computing on its own. What it did was provide a fundamentally more reliable, more efficient, and far more scalable building block, one that could eventually be manufactured by the billions on a single chip through advances in semiconductor engineering that took decades to fully develop. The transistor did not represent the finish line for computing. It represented the moment the field moved from proving a concept worked in principle to having a genuinely scalable path toward building something transformative. The new research paper argues that quantum computing has now reached that exact kind of juncture. According to the researchers behind the study, the foundational physics underlying quantum computing is now well established, and functional systems genuinely exist and work, in the same way that vacuum tube computers genuinely existed and worked decades ago. But scaling those foundational quantum systems into something reliably useful at a large scale will require the same kind of coordinated advances across engineering, manufacturing, and cross-sector collaboration that took the broader computing industry years to work through after the transistor was first invented. This is a notably more measured and specific claim than the kind of breathless quantum computing hype that has circulated for years, and that measured tone is precisely why it carries real scientific weight, rather than reading like another marketing-driven prediction. So what specifically changed to prompt researchers to make this claim now, in 2026, rather than in any of the previous years, when quantum computing was already being discussed? Several concrete developments across the industry appear to have converged around the same period, each addressing a different piece of the puzzle that has historically held quantum computing back from real-world usefulness. Perhaps the most significant shift has been the movement of quantum error correction from a purely theoretical research topic into something companies are actually beginning to deliver to real customers. Quantum bits, or qubits, the fundamental building blocks of quantum computers, are notoriously fragile and prone to errors caused by even tiny amounts of environmental interference, a problem that has plagued the field since its earliest days, and that many researchers long considered one of the single hardest obstacles standing between quantum computing's theoretical promise and any kind of practical usefulness. Throughout 2025 and into 2026, multiple companies working across different quantum computing approaches have reported genuine progress on error correction techniques that move beyond laboratory demonstrations and into systems robust enough for early commercial and research deployment, a shift that industry analysts have specifically compared to the maturing focus in classical computing's own early history, where the conversation gradually moved away from simply counting how many basic components a system had toward asking harder and more practically important questions about reliability, stability, and whether results could actually be trusted and repeated consistently. One particularly concrete example of this shift involves a company called Quantum Motion, based in the United Kingdom, which in May of 2026 raised a substantial $160 million funding round, specifically built around this exact transistor moment framing. Quantum Motion's approach is notable because rather than pursuing some of the more exotic and specialized manufacturing techniques other quantum computing companies rely on, it builds its quantum processors using silicon transistor-based architecture, essentially the same fundamental semiconductor manufacturing technology already used to produce every smartphone and laptop chip in the world today. This matters enormously for the transistor moment comparison, because it represents a deliberate strategic bet that quantum computing's path to real, large-scale usefulness runs through existing, well-understood semiconductor manufacturing infrastructure, rather than requiring the invention of entirely new and exotic fabrication techniques from scratch. According to the company, the silicon-based approach can deliver systems with roughly 100-fold reduction in cost and physical space requirements, along with a 1,000-fold reduction in energy consumption, compared to some competing quantum computing architectures. And critically, these systems are designed to fit inside standard existing data center racks rather than requiring specialized, purpose-built facilities. The company has already deployed what it describes as the world's first full-stack CMOS-based quantum computer at the UK's National Quantum Computing Centre, where it has been used for genuine early proof-of-concept work in quantum chemistry applications, moving the technology at least partially beyond pure laboratory demonstration and into a setting where real research questions are being actively explored. It is important to understand that Quantum Motion's silicon-based approach represents just one of several competing strategies currently being pursued across the broader quantum computing industry. And this diversity of approaches is itself part of what the new science paper specifically examined. Different companies and research groups are betting on fundamentally different physical systems to serve as their qubits, including superconducting circuits cooled to extremely low temperatures, individual trapped ions held in place using electromagnetic fields, photons of light manipulated through specialized optical systems, and neutral atoms arranged and controlled using precisely tuned laser light. Each of these approaches carries its own distinct trade-offs in terms of how easy the qubits are to control, how long they can maintain their delicate quantum properties before environmental interference disrupts them, and how realistically the underlying technology can eventually be scaled up to the kind of large qubit counts that would be needed for genuinely powerful, broadly useful quantum computers. The science paper's comparison across these different platforms found what its authors describe as both impressive, genuine progress and steep remaining challenges. A nuanced conclusion that avoids simply declaring any single approach the outright winner, while still confirming that the field as a whole has crossed a meaningful threshold. This diversity of competing approaches has led some industry commentators to draw an even more specific historical parallel, suggesting that quantum computing today somewhat resembles the earliest, most experimental era of classical computing, before even the transistor existed, when researchers were still working through mechanical calculating systems, electromechanical relay-based machines, and early vacuum tube computers, each representing a different technological bet about how to build a working computer, well before any kind of dominant standard approach emerged. One technology executive working in the quantum computing space put this in particularly vivid terms in mid-2026, comparing today's leading quantum systems to the AN or FSQ-7, an enormous room-filling vacuum tube computer built by IBM in the 1950s that represented genuinely impressive technology for its era while still being nowhere close to resembling anything like the transistor-based computers that would eventually follow. Under this framing, quantum computing has not yet had its actual transistor moment in the fullest sense, meaning the moment when one particular underlying technology clearly proves itself capable of the reliable, manufacturable scaling that ultimately wins out over its competitors. But the broader field has nonetheless crossed the threshold where that kind of eventual breakthrough now looks like a realistic, foreseeable outcome rather than a distant, uncertain hope. Beyond the hardware side of this story, there has also been a meaningful shift in how quantum computing is actually being used and accessed throughout 2026, which is arguably just as important to the broader transistor moment argument as any individual hardware breakthrough. A growing number of organizations are now able to access quantum computing resources through cloud-based delivery models, similar in spirit to how classical cloud computing made powerful computational resources broadly accessible without requiring every individual company to own and maintain their own physical supercomputer. This cloud-based access has enabled a specific, pragmatic pattern of early adoption among businesses and research teams exploring quantum computing's practical potential. Rather than attempting to replace their existing classical computing workflows entirely, many organizations are running their standard classical computing processes as usual, and then testing a quantum computing step specifically on the single hardest, most computationally difficult subproblem within that broader workflow. If the quantum approach genuinely helps solve that specific difficult piece more effectively, the team can gradually expand how much of their overall workflow relies on quantum resources. If it does not provide a meaningful benefit, they can simply roll back to their existing classical approach without having invested in expensive, specialized hardware of their own. This kind of low-risk, incremental experimentation represents a meaningfully more mature and practical approach to quantum computing adoption than the more speculative, all or nothing, framing that characterized much of the field's earlier hype cycles. There is also a fascinating and increasingly important relationship developing between quantum computing and the broader artificial intelligence industry, one that runs in a direction many people might not initially expect. rather than quantum computers directly replacing the powerful graphics processing units that currently dominate AI model training. The more immediate and practically significant intersection between these two fields involves using AI to help solve some of quantum computing's own remaining engineering challenges. In April of 2026, NVIDIA, the company whose GPUs currently power the overwhelming majority of AI training worldwide, announced a family of open-source AI models called Ising, specifically designed to help researchers and companies calibrate quantum processors and decode the complex error correction processes that quantum systems rely on to maintain accuracy. This is a particularly telling development because it suggests that even one of the most dominant and successful companies in classical AI computing views quantum computing not as an imminent competitive threat to its core GPU business, but rather as an emerging complementary technology that its own AI expertise can help accelerate and mature more quickly. NVIDIA has also built out broader infrastructure, specifically designed to connect quantum processors with classical GPU-based supercomputing systems, including a hardware interconnect technology and a software platform intended to let quantum and classical computing resources work together on hybrid problems, with each type of system handling the specific portion of a computational task it is naturally best suited for. This hybrid, complementary framing matters enormously for setting realistic expectations about what quantum computing's transistor moment actually means for the near-term future, as opposed to the kind of exaggerated, misleading claims that sometimes circulate, suggesting quantum computers are already outright replacing classical computing infrastructure. The honest, well-supported reality reflected in the recent research is considerably more measured than that. Quantum computers today remain most useful for a fairly narrow, specialized category of computational problems, particularly certain types of physics simulations, specific optimization challenges, and simulating molecular and chemical interactions relevant to fields like drug discovery and materials science, areas where the fundamental mathematics of quantum mechanics gives quantum computers a natural, structural advantage that classical computers struggle to replicate efficiently, no matter how much raw processing power gets thrown at the problem. For the vast majority of everyday computing tasks, including the kind of large-scale AI model training that companies like OpenAI, Anthropic, and Google currently rely on, classical GPU-based computing remains dramatically more practical, more mature, and more cost-effective for the foreseeable future, and nothing in the recent transistor moment research suggests that is about to change anytime soon. It is also worth being clear about exactly what kind of scientific claim this research paper is actually making, since the specific framing matters a great deal for understanding its real significance. The researchers are not claiming that quantum computing has already achieved what is sometimes called quantum advantage in any broad, general sense, meaning definitively outperforming classical computers on a wide, practically meaningful range of real-world problems. What they are claiming is narrower but still genuinely significant, that the fundamental scientific and engineering groundwork underlying quantum computing has matured to the point where the field's future trajectory now looks considerably more analogous to the well-understood, historically successful pattern of classical computing's own development after the transistor was invented, rather than resembling an open, uncertain scientific question about whether the entire underlying concept can ever be made to work reliably at all. That distinction between proving the foundational concept works and proving it can be scaled into something broadly useful is precisely the same distinction that separated the era of vacuum tube computers from the eventual explosion of transistor-based computing that followed, and it is exactly the comparison these researchers are deliberately drawing. Some notable individual scientific achievements throughout the past year help illustrate the kind of foundational progress underlying this broader transistor moment argument. In October of 2025, Google demonstrated what researchers described as a remarkable computational speedup, reportedly outperforming one of the world's most powerful classical supercomputers by a factor of roughly 13,000 times on a specific category of physics simulation using a quantum processor with just 65 qubits. Princeton researchers have reported significant advances in quantum chip design specifically aimed at pushing the field closer to what is called quantum advantage, the threshold at which quantum computers can be definitively shown to outperform the best available classical alternatives on genuinely useful problems rather than narrowly constructed theoretical benchmarks. Other research groups have reported meaningful advances in extending how long delicate quantum states can be maintained before environmental interference disrupts them, directly addressing one of the field's most persistent and fundamental technical challenges. Individually, none of these specific breakthroughs alone would necessarily justify the sweeping transistor moment comparison, but taken together, alongside the parallel progress on error correction, manufacturable silicon-based architectures, and practical cloud-based adoption patterns, they paint a coherent picture of a field advancing on multiple fronts simultaneously, rather than depending on a single isolated breakthrough. The financial and commercial dimension of this story is also worth examining closely because genuine market investment often serves as one of the clearest practical indicators that a technology has moved beyond pure academic interest and into something companies believe is worth betting real money on. IonQ, one of the more established publicly traded quantum computing companies, reported revenue growth of over 200% in 2025, reaching around $130 million, and the company has projected continued growth into the range of $225 to $245 million for 2026, backed by a reported order backlog worth roughly $370 million heading into the year. The company has also built up a substantial cash reserve of over $3 billion, giving it significant financial flexibility to continue funding long-term research and development regardless of near-term profitability pressures. This kind of sustained revenue growth, real customer backlog, and strong balance sheet represents a meaningfully different financial profile than the purely speculative pre-revenue state that characterized much of the quantum computing industry just a few years earlier. And it lends additional real-world credibility to the broader transistor moment argument, since serious paying customers do not typically commit significant budgets to technology that offers no genuine demonstrable value. Beyond pure computational applications, quantum technology is also beginning to find genuine early commercial traction in an entirely different but closely related field, quantum-secured communications. In 2026, Quantum Computing Inc., working alongside the telecommunications company Ciena, demonstrated a next-generation communication security system at a major optical networking conference, combining quantum key distribution, a method of using quantum mechanical properties to detect any attempt to intercept a communication, together with quantum-based authentication and traditional advanced encryption standards, into a single unified security architecture. This kind of system is specifically designed to protect against both today's conventional cybersecurity threats and the longer-term future risk that sufficiently powerful quantum computers could eventually be used to break certain widely used classical encryption methods, a concern that has been steadily growing across the cybersecurity industry as quantum computing itself continues advancing. The same company also acquired a semiconductor manufacturer specializing in photonic technology earlier in the year, expanding its own manufacturing capabilities in an area closely tied to several competing approaches to quantum computing hardware. This kind of practical, security-focused commercial application represents another concrete example of quantum technology delivering genuine, currently deployable value today, entirely separate from the more speculative long-term promise of quantum computers eventually outperforming classical machines on broad computational tasks. It is worth giving fair voice to the more skeptical perspective on all of this as well, since not every serious voice in the industry is fully convinced the transistor moment framing is being applied correctly, even among people who broadly agree the field has made genuine progress. Some industry commentators have specifically pushed back on the idea that any single current quantum computing platform, whether that is superconducting circuits, trapped ions, photonics, or neutral atoms, has yet earned the right to be called quantum computing's actual transistor equivalent, arguing instead that today's most advanced systems more closely resemble the room-filling vacuum tube computers of the 1950s than anything resembling the compact, reliable, mass-manufacturable building block that the transistor eventually became for classical computing. Under this more cautious reading, the recent research findings should be understood as confirming that the field has moved past its earliest, most uncertain phase and into a period of genuine competitive experimentation across multiple promising approaches, rather than confirming that any specific breakthrough technology has already emerged as the clear long-term winner. This is a meaningfully important distinction, since conflating the two would risk overstating exactly how far the field has actually come, even as the underlying scientific progress itself remains genuinely real and worth taking seriously. Given how many times quantum computing has been prematurely declared to be on the verge of a major breakthrough over the past 2 decades, a healthy dose of skepticism toward this latest round of enthusiasm is not just reasonable but genuinely warranted. And it is worth applying that skepticism directly to the transistor moment claim itself, rather than accepting it uncritically. The researchers behind the actual science paper appear to have anticipated exactly this kind of skepticism, which is likely why their claim is framed so carefully and specifically. They are not predicting a specific near-term date by which quantum computers will become broadly useful for everyday applications, nor are they claiming that all of the remaining engineering challenges have already been solved. Instead, they are making a more modest, historically grounded observation that the pattern of progress the field is currently exhibiting genuinely resembles the pattern that historically preceded classical computing's eventual transformation from a niche scientific curiosity into the technology that reshaped the modern world, while explicitly acknowledging that the timeline from that kind of foundational inflection point to genuinely transformative real-world impact took classical computing itself several additional decades to fully play out. This history lesson from classical computing is worth dwelling on a bit longer because it offers a genuinely useful framework for setting realistic expectations about quantum computing's own likely trajectory going forward. The transistor was invented in 1947, but it took until the 1970s for integrated circuits packing many transistors onto a single chip to become commercially practical and widespread. And it took until the 1980s and beyond for personal computers built on that technology to become genuinely common in ordinary homes and workplaces. That is a gap of several decades between the foundational breakthrough and the technology's ultimate mainstream transformative impact on everyday life. If quantum computing's own transistor moment follows even a roughly similar trajectory, the reasonable expectation should be that today's foundational progress represents an important and genuinely exciting scientific milestone, one worth taking seriously and investing in, rather than a signal that broadly transformative everyday quantum computing applications are right around the corner. History suggests the eventual payoff from this kind of foundational breakthrough can be enormous, but it also suggests that payoff typically is not immediate, a nuance that is easy to lose in more sensationalized coverage of quantum computing news, but that the actual underlying research is quite careful and explicit about acknowledging. For businesses and technology leaders currently trying to decide how seriously to take quantum computing right now, given this more nuanced picture, the practical takeaway emerging from recent industry analysis is that the window for building basic quantum readiness is arguably now, even though the technology remains far from fully mature. This does not mean every company needs to rush out and purchase expensive quantum hardware or hire specialized quantum computing teams overnight. It means that organizations working in fields where quantum computing already shows genuine early promise, such as pharmaceutical research, materials science, complex logistics and supply chain optimization, and certain areas of financial modeling, may benefit from beginning to experiment with the incremental. Low-risk cloud-based approaches described earlier, testing quantum methods on their single hardest computational subproblems while keeping their broader classical infrastructure fully intact as a reliable fallback. This measured exploratory posture reflects the genuinely transitional moment the field currently finds itself in, mature enough that serious experimentation is worthwhile, but not yet mature enough to justify wholesale strategic bets on quantum computing replacing classical approaches across the board. There is also a useful lesson here about how scientific claims of this kind travel once they leave the pages of a peer-reviewed journal and enter mainstream media and social media coverage. The original science paper itself is a carefully hedged, technically precise piece of research explicit about both genuine progress and remaining limitations. By the time headlines and video titles distill that nuanced argument down to a punchy phrase like quantum computing just hit its transistor moment, some of that careful nuance inevitably gets flattened in the process, even when the underlying reporting remains fundamentally accurate. This is a pattern worth watching for across all fast-moving areas of science and technology news, not just quantum computing specifically, since the gap between what researchers actually claimed in their original paper and what a viral headline implies is often where the most significant misunderstandings creep in. The genuinely accurate version of this specific story is exciting enough on its own merits without needing exaggeration. A serious, peer-reviewed scientific analysis concluding that quantum computing has reached a real, historically meaningful inflection point, while being equally clear that meaningful, everyday transformation from that point will still likely take considerable additional time to fully play out. Ultimately, what makes this moment in quantum computing's long and often overhyped history genuinely worth paying attention to is not any single flashy headline or dramatic demonstration, but the specific, carefully reasoned scientific argument that the field's underlying trajectory now resembles a well-understood historical pattern that has, at least once before, eventually produced one of the most transformative technologies in human history. Whether quantum computing ultimately lives up to that same scale of transformation remains genuinely uncertain, and skepticism about specific timelines remains entirely warranted given the field's long history of premature enthusiasm. But the specific, measured claim that quantum technology has reached a foundational inflection point comparable to the earliest days of classical computing, made not by marketing departments or hype-driven commentators, but by a serious team of physicists and computer scientists publishing in one of the most rigorously reviewed scientific journals in the world, represents a genuinely significant moment worth understanding clearly, distinguishing carefully between what has actually been demonstrated and what still remains, quite honestly, a promising but unproven bet on the future. If you found this breakdown useful, the story of quantum computing's slow, uneven march from theoretical physics, curiosity toward genuine practical usefulness is one of the most fascinating And consequential technology stories still being written today, and this transistor moment is very likely just one chapter in a much longer story. Keep watching how companies like Quantum Motion continue scaling their silicon-based approaches. Keep an eye on whether error correction techniques continue maturing across other competing quantum platforms. And keep watching how hybrid quantum classical systems, built through partnerships like the ones NVIDIA is pursuing, begin tackling genuinely useful real-world problems. Because those specific developments will tell us far more about quantum computing's actual future than any single dramatic headline ever could.